Okay, so let us look at this one, this example. Now we had already wrote the normal force in terms of its components. Of course, here there is something we don't know, and we don't know. So we should also solve for the magnitude of the normal force. We should write the weight vector in terms of its components. Now, to do that, let's just, the weight vector will be pointing downward. This is the weight. Or if we would show it over here, this will be the weight. So if you think of the angles over here, this angle over here is theta. What is this angle over here? That's also theta. This angle itself is also theta. So we can write the components of this vector. So what is the length of this side? You see, the length of the weight vector is nothing but mg. Now that component is just, here we have a right triangle. This is the angle we have. This is the adjacent side, so it's the cosine. This is mg cosine theta. And this side is mg sine theta. Okay, mg cosine theta is in the minus y direction. So the weight vector is mg cosine theta in the minus y direction plus mg sine theta in the x-hat direction. This is the weight vector we have. So we can write down the total force acting on my object. It's just the sum of these two forces, weight plus the normal force. So this is equal to, okay, in the x direction, we have mg sine theta. In the y direction, we have mg cosine theta minus n. This is the total force acting on my object. Now let's write the acceleration vector. Of course, we don't know its components, but we can just use some symbols just like we did over here. We don't know the normal force, the magnitude of the normal force, but we just use the symbol n for the component in the y direction. So what is the acceleration vector? What is the direction of the acceleration vector? It should be in the x, because the x-axis we had chosen to be along this inclined plane, unless the mass is just flying off the inclined plane or moving into the surface. It should be in the x direction. Minus n. Well, it's minus mg cosine theta. It is plus n minus mg cosine theta. Now the acceleration is in the x direction. We don't know its magnitude, so it should be a in the x direction. A we don't know. So let's see, this total force, now we can use the Newton's second law. This should be equal to the mass of the object times the acceleration of the object, which is a in the x-hat direction. So we have this equation that this force has to be equal to m times a in the x direction. Now we have two unknowns, two things that we have to determine. We don't know n, we don't know a. We have two unknowns, we have to come up with two equations that would relate these two. Now if we have these two vectors, they should be pointing in the same direction. Well, let's see, this vector is pointing in the x direction. This vector both has an x component and it seems that it has a y component. But if this vector has a y component, it cannot be equal to this one. If two vectors are equal, they are pointing in the same direction, they should have the same components. The y component of this vector over here is 0. So the y component of this vector should be 0. But that tells me that minus mg cosine theta plus n should be equal to 0, or the normal force should be equal to mg times cosine theta. So now we know the normal force. So this is 0, and the x components should be equal. Here we have the x component is mg sine theta. And on this line, the x component is mass times a. So we know the acceleration, the magnitude of the acceleration, it is g sine theta. Okay, we still didn't write the acceleration vector, or we didn't write the acceleration. The acceleration is g sine theta in the x-hat direction. This is the answer. If you just leave it over here, it's not yet complete. This is the acceleration. This is just the magnitude or the component of the acceleration. Now, any questions on this one? Okay, now let's get a more complicated example. Again, we have the same inclined plane, but this time we have two masses. They are attached by a string over a pulley. This has mass m1, this has mass m2. What are the acceleration of these two masses, m1 and m2? Sure, but we have to calculate it. Okay, the angle theta. I don't know. We don't need to know that. We don't need that information. So let's see. First, we have to draw the free body diagram. That's always what you have to do first. Here, in this case, we have two masses, M1 and M2, so we will have two free body diagrams. I mean, the pulley, we will assume is massless. The string is massless. So we have this mass M1, and this is the other mass M2. Yes? There's no friction. Now, what are the forces acting on M1 and M2? Let's start with M1. Okay, there is the weight. Let's call it omega 1. There is the tension force. And there is the normal force. Okay, for M2, what are the forces acting on M2? Tension and weight. Okay, there is the weight, omega 2, and there is the tension. Let's call it T prime. Is T equal to T prime, the vectors? Are they equal?
No.
Their magnitudes are equal. They are two different vectors, so that's why I have to use different signs for each one of them. I know that their magnitudes are equal because on a massless string, the tension at every point is the same, and these forces are created by the tension, so they are the magnitudes of these forces is equal to the tension on the string. Now, first let's also choose a coordinate axis. Okay, in this one I will choose two different directions. I will call this direction my x direction, and I will call this direction my x prime direction. They are not a coordinate, they don't form an orthogonal coordinate axis, they are not perpendicular to each other, but for my purposes, these two directions will be enough. You will see why. Let us also describe this y direction. Now I will need the y direction. Now let's start with the first mass, the free body diagram of the first mass. Now for the first mass, I will be using these axes. Now omega 1, or let's see, n1, in terms of its components. We don't know its magnitude yet. It's n1 in the y direction. Now for t, I don't know its magnitude. I don't know the tension. That is one thing. We don't know the tension on the string. That is something we have to determine. But let's just call it t. It will be pointing in the minus x direction. And then there is the weight. The weight is exactly as before. The weight has the same expression. So this is the weight. Omega 1 m1. So that's all I need for the first mass. Now let's look at the free body diagram of the second mass. Okay, we have omega 2. Let's say t prime. T prime is minus x prime hat. Omega 2, the weight of the second mass. Its magnitude is m2g. It is pointing in the x prime hat direction. What is the acceleration of a1? So one of you were asking in which direction are they accelerating or moving? We don't know for the time being. We don't know whether a1 is in the x direction or in the minus x direction, but I don't care. I can just say that this is equal to a1 in the x direction. This number a1 can be positive or it can be negative. I don't know for the time being. That's something I have to determine. Once I find the acceleration, I will know whether it is positive or negative. Now let's look at a2. I don't know whether it's moving up or down, but even that I don't really care for the time being. That's what I want to find out. It will be a1, a2 in the x prime hat direction. Again, I don't know whether this a2 is positive or negative. If a2 turns out to be positive, it just means that it's accelerating downward. If a2 is negative, it's accelerating upward. So what are the unknowns? Oops. So these are the definitions that I will be using. Now I had this problem. I had this inclined plane, and I wanted to find the acceleration of each one of the masses. So first I rewrote the problem in terms of some mathematical expressions. Now of course here there are many unknowns that I need to solve. I don't know a1, I don't know a2. I don't know a1, I don't know a2, I don't know n1, I don't know t, and all the rest are known. I know g, I know theta is given in the problem. And these are the things that I had to define in order to be able to describe the problem in a mathematical form. So I have to find out what each one of these are. Okay, I have 4 unknowns. I need 4 equations. So let's start writing my equations. Newton's second laws will give me most of them. Now what does Newton's second law tells me? Okay, let's look at the omega 1, the mass 1, the first mass. I have already identified all the forces acting on it. So I can just write the total force. Okay, the total force acting on 1 will be equal to, okay, in the y direction, there is the n1 minus n1g cosine theta. This is in the y direction. In the x direction, I have n1g sine theta minus t. In the x direction. This is the total force. Okay, now the second law just tells me that this is equal to m1 times the acceleration vector. Okay, the acceleration vector, I just defined it like this, a1 in the x hat direction. So this is one equation, one vectorial equation. Okay, this will lead to 2 algebraic equations. So if you look at the x component of this vector, that is n1a1, should be equal to the x component of this vector, because these 2 vectors are equal, is n1g sine theta minus t. And if you look at the y component of this vector, there is no y component, so the y component is 0. Okay, the y component over here is n1 minus n1g cosine theta. Okay, this is our equation 1, this is our equation 2. So we already have 2 equations. Or if you want, we can just solve for the second one, n1 is equal to n1g cosine theta. We already know one of them. So there are 3 unknowns left. So we need 3 equations for these 3 unknowns. This equation 2 we had already solved. So we have 1 equation. We still need to find 2 more equations. Now let's look at the free body diagram of the M2. We had already identified the forces. So the net force will be just the sum of these 2. It is m2g minus t in the x prime hat direction. The force, the total force acting on 2. Now let me just use a small t to denote the total. This is m2g minus t in the x prime hat direction. And again, Newton's second law tells me that this should be equal to m2a2 in the x prime hat direction, because the acceleration of the second mass, we know that it's in the vertical direction, and we had defined it like this. So this tells me that m2g minus t should be equal to m2a2. This is our third equation for the 4 unknowns. We still need 1 more equation. There's still 1 more information that we didn't use.
Can I just A2 is equal to minus A1
Why?
in the magnitude?
Why?
Because they move together and their velocities must be same. So when their velocity changes, it changes with the same amount, so that their acceleration should also be same.
Basically correct. You see, if you look at, they're attached to the string. We are assuming that we are not able to stretch the string. The length of the string is just constant. So that basically means that if M1 is displaced by delta R1, let's call it some d in the x-hat direction. So let's say this M2, if we move this mass M2 in this direction by an amount d, or in the other direction by an amount minus d, this will be the displacement of this mass m1. But we know that if it is displaced by d, this mass should also be displaced by the same amount d, either up or down. So if this is displaced by d this much, m2 should be displaced up by the same amount, so delta R2 would be equal to minus d in the x prime hat direction. Well, these two equalities are hold whether d is positive or negative. So these are for the displacements. If you divide by the time it takes, so you see that the velocities should be related by delta v1, at least let's say the magnitude of v1 should be equal to the magnitude of v2 all the time. And if the direction of v1 is in the positive x direction, the velocity of the m2 should be in the minus x prime hat direction. If this is going in this direction, this should be moving upward. It should also hold all the time. That basically means that if the velocities are changing, still the equality should hold, the relationship should hold, but that also means that the accelerations should have satisfied the same relationship. The only difference is that if this is accelerating in the positive x direction, this should be accelerating in the positive x prime direction. Negative x prime direction, sorry. That's why we have this minus sign over here. So this thing implies that A1 is equal to minus A2. And this is our fourth equation. Let me take these equations.
They're not moving in the opposite direction.
Hold on. We have this one. We have this one. And we also have A1 is equal to minus A2. Well, of course, they are not moving in opposite direction. That's why I'm not writing a vector equality over here. You see, A1 is the component of the acceleration of mass 1 in the x direction, and A2 is the component of the acceleration of mass 2 in the x prime direction. And I also know that if M1 accelerates in the x direction, M2 should accelerate in the minus x prime direction. That is why we have this minus sign. The component of the acceleration of M1 in the x direction, in this direction, should be opposite to the component of the acceleration of M2 in the x prime direction. There is no vector equality over here. Only in terms of the components we have this relationship. So now we have to solve these ones. The three equations for three unknowns. Well, the easiest one will be just to put this in the first two, and so that would tell you M1A1 is equal, or let's say M1A1 okay, the first expression tells me that T is equal to M1G sine theta minus M1A1 from the first expression. Well, the second expression tells me that T is equal to M2G minus M2A2, but A2 is minus A1, so it is plus M2A1. So this just tells me that if I just move M1G sine theta minus M2G, this should be equal to M1A1, M1 plus M2A1. So we know A1. M1G sine theta, or let me write it in this form, M1 sine theta minus M2 divided by M1 plus M2 times G. So we know A1. If you want, you can calculate. A2 is just the opposite of this one. And T, you can just calculate from here. We already know A1. So basically, we have solved the problem. Now, still A1 vector, the acceleration of the first one will be M1 sine theta minus M2 divided by m1 plus m2g in the x-hat direction. This is the acceleration of the first mass. So which direction does it accelerate?
Depends on the masses.
It depends on the masses. If m1 sine theta is larger than m2, in that case it will accelerate in the x-hat direction. If m1 sine theta is smaller than m2, then it will accelerate in the minus x direction. So let's see, does this make sense? So we can always look at certain limits to test whether our expressions make sense or not. For example, we can look at the case when theta is equal to 0. Now what happens when theta is equal to 0? Well, this inclined plane is not inclined, it's horizontal. So you have a mass over here, there's a pulley, there's another mass over here. So which direction should it accelerate? I have the mass over here, there is the string, the other mass is over here. What is the direction of the acceleration? Well, you see, when theta is equal to 0, this is the case we have. This is the mass m1. There is no friction. This is the mass m2. What is the direction of acceleration? Does it depend on the masses? What is the direction of acceleration? Well, you see, okay, the acceleration of m1 cannot be downward, it's horizontal. What is the acceleration of m1? In which direction does it move? It will accelerate towards the left, independent of what masses are. Well, left is the minus x direction. Left is the minus x direction, so the a1 should be negative. Well, let's see, if theta is equal to 0, this is 0, so a1 is minus m2 over m1 plus m2. Well, it's a negative number. So the a1 is negative, so the mass 1 is accelerating in the minus x direction. It is that direction in this graph. Yes? There's no friction. In this problem, we are not yet discussing friction. There's no friction. This is one limiting case where, okay, it makes sense. Well, we can look at another case when theta is equal to 90 degrees. You see, when theta is equal to 90 degrees, this is the system we have. We have the pulley, we have these two masses, m1, m2. Now, in this case, if m1 is larger, then a1 should be positive. If m1 is smaller than m2, then a1 should be negative. Well, let's see, if theta is equal to 90, sine of 90 degrees is 1. Here we see that a1 is m1 minus m2. If m1 is larger than m2, so this weight, this mass over here is larger, it accelerates in that direction. If m1 is smaller than m2, then m2 will accelerate downward, m1 will accelerate upward, and that is what we are finding over here. So at least in these limiting cases, our result makes sense. It coincides with our expectations. Yes, questions? This one. Let's look at it in more detail. Okay, this is our inclined plane. This is theta. We said that this is our x-axis. This is our x prime direction. This is our mass m1. This is our mass m2. So just for the sake of talking about an example, let's assume that m1 is accelerating in the m1 is moving in the x direction. We displace m1 in the x direction. You can either say that, okay, m1 is heavy enough, or you can say that you hold m1 and move it in the positive x direction. Our argument will not change. So then the displacement of m1 let's say it is d in the x-hat direction, the displacement of m2 will be minus d in the x prime hat direction. So if this is moving in the plus x direction, this will be moving in the minus x prime direction. So any questions on this one? But if you just divide this by the time it takes for this change to happen, we get the relation between the velocities. If velocity 1 of mass 1 is v1 in the x direction, then the velocity of 2 should be equal to v2 in the minus v1 in the x prime direction. If one is moving in the plus x direction, the other one should be moving in the minus x prime direction. And this should hold at all times. Even if v1 changes, this should still hold. So the change in v1 vector will be the change in v1 in the x direction. The change in v2 vector will be minus the change in v1 in the x prime direction. Well, divide by delta t, or multiply by 1 over delta t. This tells me that if a1 is equal to a1 in the x-hat direction, then a2 should be equal to minus a1 in the x-hat direction. Well, this is delta v1, this is delta v1, the same v1. a1 here is nothing but delta v1 divided by delta t. So here I have delta v1, this is the change in the velocity of the first mass. Here the change in the component of the velocity of the second mass should also be equal with this minus sign. If I multiply both by 1 over delta t, here I get delta v1 over delta t, which I call a1. Here, for the change in the velocity of the second mass divided by the time it takes, I have minus delta v1 over delta t. Again, delta v1 over delta t is a1. This minus sign is this minus 1. No. A1 is not the in this expression, it's not the magnitude. It's the component of acceleration in the x direction. You see, I mean, this A1 can be both positive or negative. That's why it's not a magnitude. Or if you want to be more precise, we can say the x components. But since it doesn't have any other component, I just drop this x.
What is without x hat? What is without x hat?
This A1. Well, here is our definition. Here is the definition we used. How we define A1. I mean, without this definition, if you just write me A1, I will just interpret it as the magnitude of A1. But here I made the definition of A1. You say A1 vector is just A1 in the x direction. So this A1 over here is defined as the component along the x direction. It's not the magnitude. The magnitude of this A1 vector is the absolute value of this A1. If I knew that this was positive, in that case, of course, this would correspond to the magnitude. But it doesn't have to be. Furthermore, I don't even need to know which direction the object is moving or what are the masses, which one is larger, which one is smaller. I don't need to make any assumptions on these. I just let this coefficient to be either positive or negative, and it will be my solution that will tell me whether it is positive or negative. Like?
Direction.
Yeah, I mean, if this is positive or negative, that will tell me its direction. If A1 turns out to be negative, it just tells me that it is accelerating in the minus x direction. Other questions? Okay, let's discuss another example. Well, this part we had already seen. We had this mass m attached to a string. And there's another string at the bottom Let's say that we pull this string by some force F. So there's this mass, you attach it to the ceiling. Then there's another cord at the bottom and you just pull it down. What will be the tension of the top string? Let's call the tension over here T.
Weight of the object and plus the force, the applied.
Okay, let's just solve it. There is the M. Okay, the tension on the bottom string will be the same. It will be equal to the magnitude F because the string is, we will assume the string to be massless. So there will be this force F acting downward. There will be the tension force acting upward. There will be the weight acting downward. Let's just choose the downward direction as our x-axis. So weight will be mg in the x direction. The force vector will be F in the x direction. The tension vector will be, the tension force will be minus T in the x direction. It is pointing upward. T is positive. That's why I add this minus sign over here. So the total force, which should be equal to mg plus F minus T x hat. Now, if the string doesn't break, if it doesn't break, then this should be equal to 0. So the tension should be equal to mg plus F. Now, if you increase the force, the tension should increase, but beyond the tension, for any string, it has a finite strength. So there is the maximum possible tension that it can support without breaking. So if the force F is large, then the string will break. So which one will break, the top one or the bottom one? So let's see. Prepare your phones. So you have this mass attached by a string to a wall. There is another string at the bottom, and you pull the bottom string downward. Which one will break first? And we will assume that both strings are identical. Okay, so let me give you a hint. I mean, if you had sent your answers, you cannot change it, but the hint is the answer is not A. Okay, I will stop it here. Or you can even continue sending your answers. I mean, we will be discussing this question when we have a next lecture. But there is already a demonstration of what happens. So this is our mass. There is a string over here. Well, the mass is attached by a wire so that it will not fall on the ground. But there is also a string over here that you cannot see that's holding the mass.
That's the most likely, right? 3210.
So the bottom one went down. He will try it once more.
This one's stronger, perhaps. No, I don't cheat. I got him out. Did we overlook something? You know what? I'll give you a second.
So now he's trying a second time. He attaches another string. This time it's the top one. Well, you see, pay attention of it. So you see, whenever you do experiments, and you will be probably discussing this in Physics 107, there is something we call controlled experiments. I mean, if you want to study the effect of one parameter on a phenomena, you only change that parameter, not the other ones. You try to keep the other ones fixed. There is something else he is changing in these two cases. This is one of them. What does he change in both of the attempts? His speed is different. In one of them, he just pulls it down. In the other one, he pulls it slowly. So what effect does it have?
I increased tension here.
Well, we have seen that in certain cases it's the top one, in certain cases it's the bottom one. Well, it breaks eventually, so there are only two possibilities left, either C or D. Now, we can never know, no, we can know. The answer is C. It depends on how fast we move the string. Why? Okay, that's the answer, but that's what we observe. But the real question is, why does it depend on the velocity, on the speed that we pull? I will not discuss this now. you will go for a break, but if you have any questions before you go for a break, we can discuss it now. Not about this one. This one, you have to think of it. Why does how fast we pull the string affect which one breaks? That is for you to think through this week. So in next week, we will continue.